Hey, welcome to The Explainer. Today, we're going to pull back the curtain on one of the most fundamental rules of the entire universe. It's a principle that controls how energy works everywhere and in everything. We are talking about the first law of thermodynamics.
But let's start with something you see every single day. You pour a fresh, hot cup of coffee, you get busy, and when you finally remember it, it's lukewarm. It happens every time, right? But think about this. Have you ever seen a glass of iced tea sitting on the same table suddenly decide to start boiling all by itself? No way, of course not. And that's not just a coincidence. It's a giant clue that points us straight to the law we're about to unpack.
So, here's how we're going to tackle this. First, we need to learn the basic lingo, the secret language of energy. Then, we'll get to the most important rule in its grammar book, the law of conservation. After that, we'll see how this language describes energy in action, and finally, we'll see just how this one simple rule pretty much runs our entire world.
Okay, so you can't learn a new language without learning the words first. And a fun little fact, a lot of the pioneers who figured this stuff out were Italian, so you're going to see some of the classic original terms they came up with. Before we can really get the law itself, we have to get on the same page about a few key ideas.
First on the list, heat. And right away, here's a super important point. Scientists don't talk about an object having heat. Heat is what we call energy when it's on the move, when it's flowing from something warmer to something cooler. Like the energy leaving that hot coffee of yours and warming up the air around it.
So if heat is energy that's moving, then what do we mean when we say something is hot? Well, that's temperature. Just picture it as a way to measure the microscopic chaos happening inside an object. It's the average energy of all its little molecules just jiggling around like crazy. The more jiggle, the higher the temperature. And this, right here, is the key difference you've got to get. Heat is the flow of energy, while temperature is a snapshot, a measurement of it. So one is the journey, the other is a spot check of how things are going. They're definitely related, but they are not the same thing, and understanding this difference is the key that unlocks everything else. Okay, so if heat is the energy flowing out, what do you call all the energy an object actually has stored inside it? That's what we call its internal energy. It's the grand total of all the energy of all its molecules put together, all that jiggling energy we just talked about. The easiest way to think of it is as the system's total energy bank account.
All right, now that we've got the vocabulary down, we can finally learn the single most important rule of grammar in this whole energy language. This is where it all clicks into place.
The big idea behind it all is actually beautiful and simple. You can't just create energy out of thin air, and you can't make it disappear either. All you can ever do is move it around, or change it from one type to another. It's like the ultimate cosmic accounting rule. The books always have to balance.
And here it is. This is what it looks like in the super concise language of mathematics. This little equation might look simple, but it's the first law of thermodynamics, and it is honestly one of the most powerful and important ideas in all of science.
So let's break this down real quick. That triangle U, delta U, is the change in the system's internal energy, its bank account, remember? Q is the heat you add to it, think of that as a deposit, and L is the work the system does, like making a withdrawal to go push on something. So the change in your account balance is simply your deposits minus your withdrawals. That's it. Simple as that.
Okay, so now we have the rule. Let's start speaking the language and see how this rule plays out in a few different situations, or what a physicist would call thermodynamic processes.
The real world is messy and complicated, right? So to figure it out, we create these simplified scenarios. In thermodynamics, we do this by picking one thing, like volume or pressure or temperature, and we hold it perfectly still. We keep it constant. And then we just watch to see how everything else has to change to obey the first law.
This table shows you just how the first law adapts. For example, look at an isochrona process. If you keep the volume from changing, the system can't do any work. So the law simplifies. Any heat you add, Q, goes directly into raising the internal energy, delta U. But check out an isothermal process. This one's really cool. If you keep the temperature constant, the internal energy can't change, which means every single joule of heat you add has to be instantly turned into useful work. It becomes a perfect one-to-one converter of heat into work. How cool is that?
Let's make this really concrete. Imagine we're heating up some gas in a cylinder that has a piston on top that can move freely. This keeps the pressure constant, so it's an isobaric process. Now, when you add heat, that's Q, two things happen. Some of that heat goes into making the gas molecules jiggle faster, which raises the internal energy, delta U. And the rest of that heat energy goes into doing work, L, by physically pushing that piston up. It's a perfect, real-world picture of our equation. The change in internal energy is just the heat you put in minus the work that came out.
Now, I know this might all seem like it's just about gases and cylinders and lab experiments, but trust me, the first law is so much bigger than that. It's a universal principle that's running literally everything around us and even inside of us.
That engine in your car? It's just a machine that's built to master these energy transformations, turning the heat from burning gasoline into the work that moves you down the highway. The power plant providing electricity to your home, it's doing the same thing, just on a gigantic scale. Even your own body is a thermodynamic system, constantly turning the chemical energy in your food into heat to keep you warm and into work to, move your muscles.
And at letter Q in our equation, the heat that's moving into or out of a system, it can actually travel in three main ways. It can move through direct touch, which we call conduction. It can move through the flow of a liquid or gas, like air or water, that's convection. Or it can radiate across totally empty space as electromagnetic waves, which is exactly how we feel the heat from the sun millions of miles away.
So let's wrap this all up. What are the big takeaways here? Number one, energy is always conserved. It can't be created or destroyed, it just changes its outfit. Second, remember that heat and temperature are not the same thing. Heat is the flow, temperature is the measure. Third, a system's internal energy is its total energy bank account. And finally, the first law, delta U equals Q minus L, isn't just a boring equation. It is the rulebook for tracking that energy bank account, and it's what helps us understand everything from engines to weather to life itself.
And that leaves us with one last fascinating question to chew on. If the first law guarantees that energy is never actually lost, then why can't we build a machine that just runs forever? Why can't we just perfectly recycle energy over and over again and get infinite free work? The answer to that question reveals another secret about how the universe works, one that's just as profound, and it all lies in the second law of thermodynamics. But that, my friends, is a story for our next explainer. Thanks for joining me.